Now let us demonstrate another interesting aspect of power series. So if you recall our initial discussion of what a power series is and how it defines a function, I mentioned that a power series can be thought of as an infinite polynomial. So now in the following example, we bring it even closer to the usual finite polynomial by showing how power series can be multiplied. So let us find the first three non-zero terms. In the Maclaurin series 4. The function f of x equals e to the x times sine of x. So, of course, this can be done directly if we need the first three terms from the Maclaurin series of this function. We could just easily go ahead and use the definition of Maclaurin series, evaluate the derivatives at point 0, substitute into the formula, and that would give us the terms of the series. Now, it is interesting to note that another way to do this is to treat Maclaurin series for these two functions as if they were polynomials. So let us think of it this way. F of x is the product of these two functions, right? Now, we know that each of these two has a Maclaurin series which represents it everywhere on the number line. In fact, if you recall, the radii of convergence of these two series are infinite. So what we are going to do is we will replace these two functions by their respective Maclaurin series. So if you check your notes, you will see that e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus and so on. Whereas sine x has a Maclaurin representation that starts off like so: x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Now, how do we find the first three non-zero terms? Well, we need to find the three terms with the lowest degree, right? So if you think of these two infinite power series you have here as if they were polynomials, if you had to find the three terms of the lowest degree in the product of these two polynomials, it would be sufficient to just take and use distributive properties of multiplication, just distribute this product to determine these terms of the lowest degree, right? So what we have here is 1 and x are the lowest degree terms in these two power series. So what we're going to do is we'll take 1 and distribute it over the terms of the second series. So what we will do is we will form the products 1 times x, 1 times minus x cubed over 3 factorial, and 1 times x to the 5th over 5 factorial. So that will give us x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Okay, so we get these terms. Are they the lowest order terms in the product, or will we have something else? Well, see, if we take the second term from the first series and form the products x times x and x times x cubed and x times x to the fifth, the resulting terms will have low degrees. They will have degree lower than x to the fifth. So we're going to have to do that if we want to capture all the low degree terms, right? So now let's go ahead and multiply the second term in the first series with the three initial terms in the second series. So we'll get plus x over 1 factorial, right? So you can think of this first term here as 1 times the second series. Then we have x over 1 factorial times the second series, which gives x minus x cubed over 3 factorial plus x to the fifth over 5 factorial and so on. And then finally, let us add x squared over 2 factorial multiplied with the second series. So that's x minus x cubed over 3 factorial plus x to the fifth over 5 factorial and so on. All right, now this sum must in principle be continued downwards, right? So here we wrote the first term in the first series multiplied by the second series. Here is the second term in the first series multiplied with the second series. And here is the same for the third term and the second series. Now we could proceed downwards, right? It would be an infinite sum, and we would just keep putting terms from the first series multiplied by the second series to infinity. Now we will not do that since we are only interested in the first three non-zero terms, and it suffices to observe that what's down there below, all the terms that are down there below, they all have high degrees, right? Certainly higher than what we have up here. So then what we need to do to write down the three lowest terms in this product, we just need to hunt them down. Let's see. So what do we have? So are there any constant terms? No. Right, so everything has x in it. All right. Are there any x terms? Well, yes. Right here I have 1 times x. Are there any other x terms? Well, this gives me at least x squared, this is at least x cubed, and so on. So I have only one x. Great. Are there any x squared terms? Well, this first line is not giving me any x squared terms. It has x and x cubed. The second line, though, does have x squared right here. So I have plus x squared over 1 factorial, which is just a fancy way to say x squared over 1. So that is capturing this product over here. There are no other x squares in the second line, and there are no further x squares in the third line either. So these are all the x squares we're getting. Are there any x cubes? Well, yes, right here is minus x cubed over 3 factorial. I have minus x cubed over 3 factorial. Are there any additional x cubes? Well, the second line only has x squares and x to the fourth. But the third line does give me another x cubed. So I will have plus x cubed over 2 factorial. And the subsequent terms in the third line are all of degree at least 5, right? I have degree 3 here and then degree 5 when I multiply x squared with x cubed over here. So these are all the x cubes I will have in my product, and so all the subsequent terms are of higher degree. Great, so I have successfully computed the 3 lowest terms. They are x plus x squared, and then over here I have x cubed over 6 minus x cubed over 6 plus x cubed over 2. So let me write it this way. The three lowest degree terms are these: x plus x squared minus x cubed over 6 plus x cubed over 2. And then combining these two terms, I will get plus x cubed over 3. So by bringing them to the common denominator, I have x plus x squared plus x cubed over 3. Because 1/2 minus 1/6 gives me 1/3. And so I have found the three lowest order terms in the Maclaurin expansion of this function. Now, is this method easier than just using the definition? Well, I would argue that it's certainly not much harder. So evaluating the first several derivatives of this function is not particularly pleasant. You need to use product rule. There is no nice periodicity in terms of derivatives as we had for e to the x and sine to the x. So computing these two expansions is much easier than the one for this product. And especially if you already know the Maclaurin expansions for e to the x and sine x, which you certainly should know, then doing this computation is fairly straightforward, and you can quickly get the answer to this question of finding the three lowest degree terms in this product right here. So yes, I would say that this method is certainly competitive as compared to using the definition of Maclaurin series.